Welcome back. In this class, we're going to talk about the thermochemistry calculation, which comes up in question 6 on the exam paper. Typically, this question is worth 12 marks in the exam, but in the past, it has come up for more marks. In 2019, it was worth 17 marks in total because students had to do an extra step at the end, which is why we're going to cover that particular question in the worked examples later on. Now, basically, for this question, all you have to be able to do is use the heats of formation to work out either heat of reaction or heat of combustion, or you are given the heat of reaction or heat of combustion and you have to work your way back to find heat of formation. So there's two ways that this question can come up. Right, so before we can do the calculation, we need this formula here, which is the sum of the heat of formation of your products minus the sum of the heat of formation of your reactants. Now, when it comes to this calculation, some of you might do this with the heat of formation or with the formation equations. I'm not a big fan of that because it's a lot of work and you don't get marks for writing the equations. So I'm going to show you how to do this that gets my students marks every single time they do it, and you're more likely to get full marks in this question if you do it the way that I'm going to show you. But if you understand and can follow what you're doing with the formation equations, then absolutely crack on, keep doing it that way. If you get full marks every time, that's absolutely fine. But I will say this, I've been correcting papers now for a long time and I've corrected in well over 1,000 papers. I have never corrected a single exam paper where a student got full marks in this question if they did it using the formation equations, because they always forget to flip the sign of something that's on the left-hand side of the equation. Always. Whereas if you use this formula, that addresses the problem of the science already for you. And it's one of the reasons why I strongly recommend it. Now, before we begin, we're going to recap the heat of formation definition. So this is the heat change when 1 mole of a substance in its standard state is formed from its elements in their standard states. But the key idea here is that we're dealing with 1 mole. Now, when we look at balanced equations, we're not going to have 1 mole of each substance. You might have 1 mole of something, but not of everything. So that is actually significant and has to be taken into account. Right, so let's start with our first worked example. Now, whenever you're tackling one of these questions, I recommend you start with a fresh A4 page. It's not going to take up the whole page, but I don't want you transferring numbers from the previous page to the next page when you're doing this calculation. Because if you're doing a calculation and you start moving numbers from one page to another, transposition errors occur, and that's where suddenly a 3 becomes a 6 and you wrote it down wrong. So we're going to try and minimize errors like that and keeping the calculations on one page. So we go to a fresh A4 page, and I'm going to read down through this question now, and I recommend that you have as many different colored highlighters as you can. One of the most common mistakes here is people mixing up what number that the number in the question goes, which substance does it go with. So we're going to get around that by highlighting the substance and highlighting the number in the same color, so you're not going to mix them up. Right, so this question, calculate the heat of combustion of methane thiol according to that equation. Now, it's worth noting you're never going to be asked to write a balanced equation like that because it contains a thiol and you've produced sulfur dioxide on the right-hand side. You don't have to be able to write combustion equations like that. The heats of formation of methane thiol, carbon dioxide, water, and sulfur dioxide are those 4 numbers respectively. Now, the word respectively means this. The first name that we see here is methane thiol. That means the first number that we read, its heat of formation is for methane thiol. So that's the minus 22.8. Then the second name that we see is carbon dioxide. The next number is for the carbon dioxide. Then we keep working our way across. We have water, and then the number for the heat of formation of water. And then the last one is sulfur dioxide. And then the last number that we see is the heat of formation for sulfur dioxide. Okay, so we've got 4 substances and 4 numbers. Now, if we look at the balanced equation, there's 5 substances in that balanced equation. It doesn't mention anything to do with oxygen, and that's for a reason. The heat of formation of an element in its standard state is 0. That's why the heat of formation of the oxygen is not given, because it's 0 and it's not going to affect the calculation. So if it's not given, completely ignore it. Now, we're asked to calculate the heat of combustion. Now, I need you to get in the habit of reading the question carefully, because if you are calculating the heat of combustion, that's the amount of energy released when 1 mole of something reacts or combusts in oxygen. That'll be significant later on, and I'll show you why. Now, what I recommend you do is, we're going to go down to here, and you on your fresh A4 page, you're going to write out the full balanced equation that you see from the question. So we have methane thiol, which is CH3 SH plus O2 to give me carbon dioxide plus water plus sulfur dioxide. Now to balance, I need a 2 in front of the water and a 3 in front of the oxygen. Now, to help me with this and making sure I don't mix up what number goes with what, if we go back up here to where we highlighted everything, I'm going to write the heats of formations given in the question underneath the substance in the balanced equation. It takes me an extra second to do this, but it is well worth it, and we don't want to be making the silly mistake of mixing up what number goes with what. So first up, we have methane thiol, which is minus 22.8. We're not given anything for oxygen, so ignore it. Then carbon dioxide is minus 393.5. Water is minus 285.8. And then for the sulfur dioxide, minus 296.8. Now, we're finished with the question, so I'm going to move this now up to the top of the page. Now, to do this, we have a formula. The energy change for this reaction is equal to the sum of the energy of the products minus the sum of the energy of the heats of formation of the reactants. Now, we don't know what the sum is yet, but we're going to find out. So I'm going to do this as a table. I'm going to draw myself a little table. Now, as you'll notice, I'm not using a ruler for this because you're not getting marks for neatness here. We're just going to, oh my God, that's not a straight line. But anyway, now I recommend in the table, you write the products on the left-hand side and the reactants on the right. The reason for this in the formula is it's products minus reactants. So that way we're not going to mix them up. And I'm going to make a list of my products. My first product is carbon dioxide. Now, the heat of formation of carbon dioxide is this number here. When 1 mole of carbon dioxide is formed, 393.5 kilojoules of energy is given out. And it's exothermic because it's minus. Now, from that balanced equation, how many moles of carbon dioxide are formed? Look at the number in front. You have a 1 in front of the carbon dioxide. So what we need to do here is we take the number in front of the carbon dioxide and you multiply it by the heat of formation. That's going to be 1 multiplied by minus 393.5, which is minus 393.5. Next, my second product is water. Excuse me. Now, in this balanced equation, when 1 mole of water is formed, 285.8 kilojoules of energy is released. However, from this balanced equation, there's 2 moles of water being formed. So we take the number in front of the water, which is 2, and we multiply it by the heat of formation of water, which is minus 285.8. When we multiply those two numbers out, we're going to get minus 571.6. My next product is sulfur dioxide. When 1 mole of sulfur dioxide is formed, 296.8 kilojoules of energy is released. So we take the number in front of the sulfur dioxide, which is 1, and we multiply it by the heat of formation of the sulfur dioxide. So it's 1 multiplied by minus 296.8, which is minus 296.8. Now at this point, I actually have 6 marks. I'm halfway to the answer. I'm halfway to the end. Now where those 6 marks are, for getting minus 571.6 correct, that number there, that's 3 marks. And then for having both of the other two numbers correct, the minus 393.5 and the minus 296.8, that's another 3 marks. Now, when I put my numbers into this equation up here at the top, I need the sum of the energy of the products. I'm not going to substitute 3 numbers into that because I find I make silly mistakes when I do that. So to get around that, I recommend that you add these numbers together now. It's not going to get us more marks. However, it's a way of making sure that you don't make slip marks. So when I add those together, I get minus 1261.9 kilojoules. Next up, we're going to deal with the reactants. So there's only one reactant that we care about. It's the methane thiol. You take the number in front of the methane thiol, which is 1, and you multiply that by the heat of formation of methane thiol. So this is going to be 1 multiplied by minus 22.8, which is minus 22.8. Now we haven't gotten any marks for that. We're going to get marks for doing something with that number. Now we have everything that we need to substitute into the heat of formation equation. We have the sum of the energy of the products minus the sum of the energy of the reactants. So we're going to take these two numbers here. So this number, the minus 1261.9, that's the sum of the energy of the products. Put it in brackets, minus the sum of the energy of the reactants, which is this number here, the minus 22.8. This is your next 3 marks. If the examiner sees minus 22.8, they're going to give you 3 marks. If you rewrite that as plus 22.8, that's also worth 3 marks. It's the same thing. Then on your calculator, you come in and you type that in, and you're going to get minus 1239.1 kilojoules. And at this point, that's your last 3 marks. But I need you to check something here. When you get down to the end of this, we need to check, have we actually worked out the heat of combustion? Because the question said calculate the heat of combustion, that's the heat released when 1 mole of something reacts. When it specifically asks you for the heat of combustion, you need to go back to the balanced equation and check the number in front of the thing that is combusting. So if we go back to the balanced equation and look at methane thiol, up here you have a 1 in front. So yes, that number that we have worked out is the heat of combustion because 1 mole of methane thiol reacted with 3 moles of oxygen. If there was a number in front of the methane thiol, like a 2, the number that we have calculated here would be the energy released when 2 moles of methane thiol reacted. Technically, that would actually be the heat of reaction because it's based on the balanced equation. And if it asked you to work out the heat of combustion, you would need to take the number in front and divide what you have worked out by the number in front, because that will then work it back for the heat released by 1 mole of something. Now, we will see a question like that in a minute. Right, next up, this is the very question. This is the exam question from 2019, where it was worth 17 marks. Tetraethyl lead burns completely according to that equation. The heats of formation of tetraethyl lead, carbon dioxide, water, and lead oxide are those 4 numbers respectively. Calculate the heat of reaction for the combustion of 1 mole of tetraethyl lead. The examiner was helping you here in 2019. She specifically said calculate the heat of reaction for the combustion of 1 mole. What she's asking you to do in a roundabout way is to work out the heat of combustion. But she knew that if she said calculate the heat of combustion, most students would forget to work it back to 1 mole. So instead, she put it in the question. And still, I'd say 90% of students forgot to do it at the end. But we'll get there. Okay, so I'm going to highlight each of my substances. I have tetraethyl lead. The first number is 52.7, so that goes with the tetraethyl lead. Then I have carbon dioxide, and then that's minus 393.5. Water, minus 285.8. And then the very last one, we have lead 2 oxide. And that is minus 219. Now, I will say at this point, because it came up quite a bit last year actually, when we were correcting, don't round the numbers that are given in the question. I had quite a few students when I was correcting that would round to minus 285.8 to minus 286. That is not allowed, and you will lose 3 marks for doing that. You have to use the numbers that are given in the question and don't round them just to make life easier for yourself. It actually doesn't in the long run, and it will cost you marks every single time that you do it. Right, so I recommend we write out our balanced equation in the space underneath. You're going to do it on a fresh A4 page. If you want to fill in an answer as I'm going through this so that you're getting used to this instead of just reading it from page 285 of your notes, I have put in the exam questions into the textbook. So if you have a hard copy of the textbook, you can fill this in as we go. Right, so I'm going to write out my tetraethyl lead. We have 2 times C2H5 with a 4 outside with Pb plus 27O2 to give me 16CO2 plus 20H2O plus 2PbO. Right, so there's my balanced equation with quite large numbers, so we've got quite a bit to do here. So I'm going to take the numbers that I highlighted in the question and fill them in underneath. And we've got 52.7 under the tetraethyl lead, nothing for the oxygen because it's 0. Then we have minus 393.5 for the carbon dioxide, minus 285.8 for the water, and minus 219 for the lead oxide. Now, same as before, we're going to have to work out the heat of reaction. So I still need my formula. My formula is delta H is equal to the sum of the energy of the products minus the sum of the energy of the reactants. So we're going to fill in our table. I'm going to put the products on the left and my reactants on the right. My first product that I fill in is carbon dioxide. Now, that minus 393.5 is the amount of energy released when 1 mole of carbon dioxide is formed. According to this balanced equation, though, I'm not forming 1 mole of carbon dioxide. I'm forming 16 moles of it. So we take the number in front of the carbon dioxide and I multiply it by minus 393.5. So that's going to be 16 multiplied by minus 393.5. Now I'm going to do this on my calculator as I go. So minus 393.5 multiplied by 16 is minus 6296. And we get 3 marks for that number. My second product is H2O. Now, same as before, we take the number in front of the water, which is 20, and we multiply it by the heat of formation. That's 20 multiplied by minus 285.8. So minus 285.8 multiplied by 20 is minus 5716 kilojoules. That's my next 3 marks. My third product, we have lead oxide. You take the number in front, which is 2, and you multiply it by the heat of formation. So that's 2 multiplied by minus 219, which is minus 438, which is another 3 marks. Right, so all in all, so far, I have 9 out of my 17 marks. Now remember, we have to get the sum of the energy of the products. So I'm going to add those 3 numbers together now before I do anything else. And that gives me minus 12,450 kilojoules. Now, we don't get marks for writing minus 12,450, but we're going to get marks for using it in a minute. Then my reactants, I have my tetraethyl lead, which is C2H5 with a 4 outside and Pb. Now there's a 2 in front of that tetraethyl lead, so I need to take the number in front and multiply it by the heat of formation of tetraethyl lead, which is 52.7. 2 multiplied by 52.7 is 105.4. Now we don't get marks for the 105.4, but we're going to get marks for using it. So now we're going to take all of these numbers and substitute them into the equation above. So the heat of reaction here, the delta H, is equal to the sum of the energy of the products, that's the minus 12450. Make sure you use brackets, minus the sum of the energy of my reactants, which is 105.4. If your examiner sees minus 105.4, that's your next 3 marks to bring you to 12 out of 17. Then on your calculator, you add that together and we get minus 12,555.4 kilojoules. That's another 3 marks. Now, if you add all of that together, you're now at 15 out of 17. So there's another step that we're going to have to do. What is that number? So based on the balanced equation that you see at the top of the page, when 2 moles of tetraethyl lead completely reacts in oxygen to form those 3 products, 12,555.4 kilojoules of energy is released. That's when 2 moles react, because you can see a 2 in front of the tetraethyl lead in the equation. I want what 1 mole is. So we need to take this number in front of the tetraethyl lead down here, and you divide the answer that I've just got by the number in front of the tetraethyl lead. And when we do that, so minus 12555.4 divided by 2 is minus 6277.7 kilojoules per mole. And that is your last 2 marks for this question. If the question had just asked you to work out the heat of reaction and it didn't mention of 1 mole, then your answer would be minus 12,555, because that's based on the balanced equation. However, if the examiner ever asks you to work out the heat of combustion or the heat of reaction for 1 mole, then you have to take your number that you've just worked out and divide by the number in front in the balanced equation of the thing that combusted. So I'm actually going to label these here just to kind of distinguish them for you. That number there, that minus 12,555, that is the heat of reaction for 2 moles of the tetraethyl lead. And this number down here, the minus 6277, that is, you can call it the heat of reaction of 1 mole, because you've divided by 2, or technically you can give it its proper name, which is the heat of combustion. Now, the reason I wanted to do that one is I wanted to point out when you need to divide by the number in front and when you don't. If the question was just calculate heat of reaction and it didn't specify for 1 mole, then you would leave your answer as minus 12,555.4. But if it asks you for the heat of combustion or the heat of reaction of 1 mole, you need to look back at the balanced equation at the number in front of the thing that's combusting, and divide your answer by the thing in front of the thing that's combusting in the balanced equation. So if there's a 2 in front, you divide by 2. If there's a 10 in front, you divide by 10. Now the next one, this one's a little bit different, because in this exam question, you are given what we have worked out previously. You're given the heat of reaction. So, the combustion of cyclohexane C6H12 may be described by the following balanced equation. Given that the heats of formation of carbon dioxide and water are those 2 numbers respectively, calculate the heat of formation of cyclohexane. Now, see the way your delta H is written here. That means the heat of reaction for that balanced equation is minus 2,710 kilojoules. So when your cyclohexane reacts with oxygen to form carbon dioxide plus water, that is the amount of energy released. Now, I will say this, if you have a hard copy of the textbook, there is a typo for this worked example in your textbook, and this is the correct question that should be there. The one that's on the platform has been updated to include the question that I have on the screen. It's just the earlier copies, I mustn't have saved it properly when I was typing it out. So anyway, we're just going to live with it and we're going to go with it. Okay, so what we have to do here now, I'm going to do the same as before because I'm a creature of habit and I like to have steps that I follow. So what I'm going to do is, same as before, I'm going to write out the balanced equation in the space below. So I have C6H12 plus 9O2 to give me 6CO2 plus 6H2O. Now, write the heats of formation underneath. So my carbon dioxide is minus 394 and the water is minus 286. Now, I'm using the rounded values here, which is fine if the examiner rounds it for you, but you don't make the decision to round it for yourself. And we're asked to work out the heat of formation of the cyclohexane. Now, same as before, we're going to use our delta H is equal to the sum of the energy of my products minus the sum of the energy of my reactants. However, we're told in the question what this value is. That's what this number up here is. So we know that the answer that we're aiming for is minus 2710. And we're going to find these two numbers in the same way as before. Okay? Now, because I'm looking for the heat of formation of the cyclohexane and we don't know what it is, I'm going to give it an arbitrary symbol. You can call it whatever you want. I'm going to call it X and we're going to go from there. Okay? Right, let's move this up to the top of the page and go at this in exactly the same way as before. I draw myself a little table. I put the products on the left, reactants on the right. A common mistake that students make here is reactants minus products. So I'm getting around that by doing it this way every single time. I have carbon dioxide as one product. You take the number in front of the carbon dioxide and you use that to multiply by the heat of formation of carbon dioxide. That would be 6 multiplied by minus 394. When I have 6 minus 394 multiplied by 6, that is minus 2364 for 3 marks. My next step is to take my next product, which is water. Again, you take the number in front of the water and you multiply it by the heat of formation of water, which is 6 multiplied by minus 286. Minus 286 multiplied by 6 is minus 1716, which gets me another 3 marks. Now, I'm going to get the sum of them here, so I'm going to add them together now. So that's that. Minus 2364 minus 1716 is minus 4080 kilojoules, if you prefer. Now, let's look at the reactants. The only reactants that we're given any information about or asked about is C6H12. The heat of formation of oxygen is 0, so we're not going to use it for anything. Now we're calling the heat of formation of the cyclohexane X. But it's what X? Same as before, you take the number in front of the cyclohexane, which is 1, and you multiply it by the heat of formation of cyclohexane. So that is 1x, or if you prefer, just call it x. Now, the reason I'm emphasizing that is it might not be 1 in front. If that was a 3 in front of the cyclohexane, then I would have 3x here when I'm writing down this value for the reactants. You always take the number in front and multiply it by the heat of formation. Now, we're going to take this and substitute in. So we have minus 2710 kilojoules is equal to the sum of the energy of the products, which is minus 4080, minus the sum of the reactants, which is X. Now, at this stage, we're not quite there yet. We have to do a little bit of rearranging to get to my final answer. So I'm going to solve for X because that will work out what the heat of formation of the cyclohexane is. So I'm going to add x to both sides. That gives me x is equal to minus 4080. Gets rid of the x from that side. And then I add 27110 to each side. Plus 2710. Now, here, for having plus 2710, that's going to be your next 3 marks. Then on a calculator, add those together. You have minus 4080 plus 2710. That works out as minus 1370 kilojoules per mole, technically, because there's a 1 in front. So it's 1x is equal to that. So that's the heat of formation of 1 mole of it. Okay, so that is your next 3 marks to get us to 12. Okay, now I'm just going to pause here for a second because I know some of you who've been doing this with the formation equations will be looking at this going, it's very short. Is that all I need to do? Yes. If you look at the mark scheme for this calculation, it doesn't matter how far back you go. The same thing is in bold in the mark scheme every single time. It's just the number. So if I'm reading down through your answer and I'm going to give you full marks, the first thing I will check is the final answer. If I see this number on your answer booklet, minus 1370, I'll give you the full 12 marks and move on. There's no point in going through it because you obviously did it right to get that number. If that's not correct, then I will start looking for the 4 or the 3 other numbers. And if I can't find them, then I try and figure out why. But when it comes to this, it's the numbers that your examiner is looking for. They don't care how you did it. But it's worth showing your workings like I have done on the screen, because if you make a small slip, let's talk about slip marks. When I took carbon dioxide, and I have 6 of them, so I'm up here. So I have 6 multiplied by minus 394, which was minus 2364. Say, for example, I didn't get that. Say I got minus 2410. Now that's a real slip. I would still get 2 out of 3 marks for the way that I have shown my workings. The calculation is correct. I have correctly written 6 multiplied by minus 394, so the operations are correct. But when I was typing that into my calculator, my finger slipped on the calculator, giving me minus 2410. The examiner will still give you 2 out of 3 marks. They only take 1 mark away for slips like that. But your examiner has to be able to see where the mistake is. And if they can't see it, they can't give it. So if I had done my answer differently, where I had come along and written just minus 2410, an examiner would be looking at that number going, that number is completely wrong. Where on earth did that come from? And they give you 0 marks for that. So it's worth, with these questions, writing out how you got to your answer. And please don't be the person that does this all in their head or on a calculator, because if you make even so much as 1 slip, you're going to lose all 12 marks here. So make sure your calculations are shown on the paper. Do you have to use a table? No. Do you have to write the formula? No. As long as your operations are correct and shown on the paper, that's all we're looking for. But the way I'm showing you here on the page in front of you is the way that all of the other examiners will do it as well. And that's going to get you more marks in the exam. That's the aim with this, is to see if we can get you the full 12 marks with this, because actually there's not many students that can get the full 12 marks here. So you'll set yourself apart by building up more marks in this question if you can nail this calculation down. Right, let's look at our last worked example. So this is worked example 4 from your notes. Propene burns according to that equation. The heats of formation of propane, carbon dioxide, and water are those 3 numbers correctly. Calculate the heat of reaction and the heat of combustion. Those 2 things are not the same. So let's highlight our numbers. We have propene, and its heat of formation is the first number that we see, which is minus 20.6. Then we have carbon dioxide, and that's minus 393.5. Then we have water, and that's minus 285.8. And we're looking for the heat of reaction. Now, same as before, let's move this up out of the way. Write out your balanced equation, 2C3H6 plus 9O2 to give me 6CO2 plus 6H2O. And we write the heats of formation underneath each substance in the balanced equation. Propene is minus 20.6. We're not given information for oxygen. Carbon dioxide is minus 393.5. And water is minus 285.8. Now your heat of reaction is worked out by the sum of the energy of your products minus the sum of the energy of your reactants. So let's move this up. So I'm going to make myself a little table. We have products on the left, reactants on the right. We have carbon dioxide. Now you take the number in front of the carbon dioxide and you multiply it by the heat of formation of carbon dioxide. That is 6 multiplied by minus 393.5 on a calculator. Minus 393.5 multiplied by 6 is minus 2361 for 3 marks. My next one, we have water, which is H2O. You take the number in front of the water and you multiply the heat of formation by that number. 6 multiplied by minus 285.8, which is minus 1714.8 for 3 marks. Then we add those together, we get the sum, which is minus 4075.8. Now, that's the sum. Now let's look at my reactants. I have C3H6 for the propene. You take the number in front of the propene and multiply it by the heat of formation of propene. 2 multiplied by minus 20.6. Minus 20.6 multiplied by 2 is minus 41.2. Now we're not getting marks for that, we get marks for substituting. So my delta H, substitute them into the equation above, use brackets, minus 4075.8 minus the sum of my reactants, minus 41.2. For minus 41.2, we get our next 3 marks. If you prefer to rewrite that as plus 41.2, that's absolutely fine. Then, when we add those together on a calculator, so minus 4075.8 plus 41.2 is minus 4034.6 for 3 marks. Now, what is that number? That is the heat released according to the balanced equation as it is asked in the question. That is number 1, the heat of reaction. When you work out the energy released according to the balanced equation, it's the heat of reaction. However, you're also asked for the heat of combustion. Now remember, for the definition for heat of combustion, it's the heat change when 1 mole of a substance is completely burned in excess oxygen. That's not 1 mole. That is 2 moles. Because when you look at the balanced equation for the propene, you have a 2 in front of that balanced equation. So when 2 moles of propene reacts, that's the amount of energy released. I want the heat of combustion, which is the heat released for 1 mole. You need to take the minus 4034.6 and you divide by the number in front of the propene. So we take this number in front and then we bring that down here and divide by that number. That's going to be minus 2017.3 kilojoules. And that will be my next 3 marks. I have a funny feeling I wrote that as plus 20.6 when I was doing the previous class, but anyway. Right, and that is the difference between heat of reaction and heat of combustion, just in case the examiner asks you a question like that. Right, that's it for the calculation. Now, I know I'm probably doing it slightly differently to how some of you are used to doing it. So that's why in the notes, if you look through the book, on page 288, that's where they start. There's about 15 pages of practice questions, and I've given you a full A4 page to work your way through them. If you sit down and work your way through these questions, you're going to have no problem with this because you're doing the same thing over and over and over and over again. And once you get used to the process, it's going to make this an awful lot easier so that when you sit down and during the exam, you're on autopilot when you're answering these questions. Now, I do want to point something out. There are some questions that have come up in the past where the examiner didn't give you the balanced equation. And part of the answer that they had to write was to write a balanced equation for a combustion reaction. So it's really important, if you intend to answer this question in the exam, that you can write combustion equations. But this is where, remember respiration. Respiration is a type of combustion. Glucose plus oxygen to give me carbon dioxide plus water. Just take out the glucose and put in the hydrocarbon or the alcohol that they're saying is combusting. Now, you only have to be able to do that for ethanol, methanol, and the common hydrocarbons. So make sure you know your general formula for alkanes and alkenes so that you can quickly write the formulas. And that's it. Right, hopefully that is helpful. Now, to help you with this a little bit more, I am going to film myself going through past exam questions for question 6, and the calculations will also be in there as well. I'm just not filming them separately because I want to do them as a whole exam question. So when you're going through these questions, they're all exam questions in your book. If you get stuck with any of them, I will be filming something to show you how I worked through it. But you'll also find the answers on page 303 in the book. So if you just flick forward to the very end of the topic, you will find them all listed out. And they will also be, because they're exam questions, there's a method to my madness. I know it never seems like it at the time. I deliberately put exam questions in there so that if you get stuck and you're like, oh, what do I do with that? You can go and look up the mark scheme for that particular year if you're waiting for me to put up the videos of me going through the exam questions. Right, hopefully that's helpful. Now you're on the right track to getting 12 marks in that calculation in the exam.